Alright, so in the previous two classes I have talked about the nature of the course structure, the various things, and also I have introduced some concepts, some broad prospectus of the world and the country in terms of the energy. Now today in this lecture we will talk about the microgrid systems and its structure, how it works, what are different components and entities which are functioning in the whole system. This I have described in the last class also, but just to give the more completeness, I am starting with this. So as I said, this microgrid is a quite mix of distributed energy sources, power electronic converters, and its interface with the grid. Then there is kind of a storage which try to buffer the energy to increase more reliability, the more availability of power under stringent conditions, under the critical conditions when the grid is not available. So this is a general structure of the microgrid, which consists of the AC grid, then there is a DC grid here. This is DC grid, this is the AC grid, and they are interfaced through appropriate converters accommodating the renewable energy sources like solar, fuel or wind, supplying the local AC and DC loads, okay, the micro turbine, and on the AC side we have a micro generator, AC utility power system, and wind power, which is AC to AC, and of course AC. Now if you look this general structure, it can be categorized in various configurations. We can broadly classify these microgrid systems either AC coupled hybrid microgrid, or you can say DC coupled hybrid microgrid, depending upon the emphasis of the bus. In case of the AC coupled, the emphasis is on AC bus. DC bus is used, but it is not very integral part of the structure. This scheme is easy to simple in structure and easy to control, but it's difficult to address the ancillary services such as power quality and load balancing through the converters. In case of DC coupled, the emphasis is on DC bus, and you can see here this is a DC bus, okay. So DC bus is more emphasized, and the AC is used to interact with the power on the DC side. So all distributed energy sources, okay, are converted to first DC bus through appropriate converters. For example, for wind turbine we have a AC to DC, for solar we have a DC to DC, okay, for storage again DC to DC, for battery DC to DC, fuel cell DC to DC. As I said, either there are DC or AC type of sources. So we need appropriate DC to DC or AC to DC or DC to AC converters on AC and DC side. This microgrid system can support both AC and DC loads. The even DC coupled hybrid microgrid can support both. And ancillary services can be easily addressed with the help of this configuration. AC-DC coupled, I have told in the beginning, some more generalized microgrid structure where we have both bus equally participating and maintaining the whole operation of the system in a close coordinated way. So this is the mix of AC and DC, functionality wise as well as the operation wise. Now one of the most important part of the microgrid, another important part of the microgrid system is the storage system, because storage plays a significant role in achieving the power balance between the renewables, the local load and the utility grid. This is required to fill the gap of intermittent nature of the renewable energy sources. unpredictable nature of load and availability of the grid. So the proper designing of the storage system makes a lot of difference in microgrid system nowadays. Because if the storage is properly designed to take care of the critical, intermittent and uncertain nature of the renewables, then it is significantly satisfy the need of the load. There are many kinds of storage system, mechanical, thermal, like inertia system is mechanical system, thermal storage another system, electrical storage another system. So in this particular course we will talk about electrical storage, not other storage. And as you know, the batteries are the predominant entities used for storage. Apart from that, supercapacitors, which have high energy density in terms of the if you compare with the normal capacitors, of course they have very high power density. In many applications, the combination of the supercapacitors and the batteries are used because they complement the each other's merits. We will see it later. As I said that these two energy devices, that is battery and supercapacitors. So just to compare these, their functions, their figure of merits or their properties, I have put this slide to understand. Now as you can see from the slide that supercapacitors have high power density. It means that for a given volume they can handle more power, while as the batteries have a high energy density. Now what is the difference between the power density and energy density? Power is the rate of change of energy. Okay, P is equal to dE by dt. So density is common anyway per volume or per mass. So it means that the dE by dt is better in supercapacitors than batteries. Okay, and lithium ion batteries have the high energy density and moderate power density. So battery in general have a more energy density, and the combination of these two energy storing devices, that is battery and supercapacitors, can fulfill both high energy density and high power density requirements. As we can see from this graph here, okay, the x-axis is power density, the y-axis is energy density. So you can see it here. For energy density, the lead acid batteries, okay, fuel cells, they are on this side. While as if you go on the high power density, then we have a double layer capacitors, ultra capacitors are here, which are also called as supercapacitors, and aluminum electrolytic. Okay, so they have a high power density, and also their timing, the charging and discharging timing are displayed here. Batteries, when you go to battery, as you go for the battery at the high energy density, the response time is little slow in hours. If you go on this side, then you see the response time is faster. Response time means charging and discharging time, how fast they can charge and discharge. You can see it here. For a supercapacitor, the energy density is 1 to 10 watt hour per kg, and for the lead acid, the energy density is 10 to 100 watt hour per kg. So you see the difference of 10 times. Okay, so energy density of lead acid battery is 10 times the energy density of the supercapacitor. Now if you come to power density, the power density of supercapacitor is 10,000, which is 10 times of power density of the lead acid batteries. Okay, so energy density is 10 times more for a battery, and power density is 10 times more of the battery for supercapacitor. So they have a complementary functionalities. So when we add them together, it makes a very nice storage system in terms of the energy and power density. Cycle life for supercapacitor is very high, okay, almost 500,000 times, and battery is 1000 times. The charge and discharge efficiency is very high for supercapacitors, and fast time charging for supercapacitors, it is in 0.3 to 30 seconds. Similarly, the discharging time is 0.3 to 30 seconds, but it is in 0.3 to 3 hours for a batteries. Okay, so you see that how the combination of the batteries and the supercapacitor make it an ideal storage system for a electrical system based microgrid systems. Alright, how these units are connected to the microgrid are shown in these figures. We may have a different combinations of the connections of the battery and the supercapacitor unit. So you can go through this. I have given the reference 5 where you can go and study, but the point is that either we can combine them together and have one common direct to load. In that case there is no controllability, and the last case has the highest controllability because we can control the battery and supercapacitor together, and finally we can control the whole unit together through the load. So in between there are other combinations that you can study. Now coming to the power flow in a microgrid system, how this takes place. So this is shown here. This is the DC bus here, and this is the microgrid voltage source converter, and this is the AC bus. So grid is this side. Okay, so BG is the grid, and there is a relay. In case of fault on the grid side, the relay can be turned off, and hence the microgrid is isolated, and it can work in the standalone mode to supply the load. Power flows between these units. For example, if we have a PV system, the power can always flow from this to this. So PV power always goes into the grid or into the load. The supercapacitor and the battery, these are bidirectional power flow. It means the power can either come to them or it can go to the grid or to the load. Then there is a DC load bus here. This is the main inverter which is used as an interface between the DC side and the AC side. So this converter can act as a rectifier as well as an inverter. If the power flows from this to this side to storage, it is become rectifier. If power goes from this to this side, become inverter. Okay, so its functionality is very high. This main microgrid converter functionality is very high. And apart from that, many additional features can be embedded to address the power quality and any other ancillary services which are required at that point of time. Okay. So this is the power flow description, and here again I have shown the more detailed schematic of the DC-AC microgrid system. As you can see, grid lies here, and this whole thing is microgrid actually. If you look from this side, this is the microgrid. Okay. So on the left side of the AC bus or the grid system, we have a microgrid which consists of the main inverter, this green color block, and this is being connected on further left side as a DC to the DC bus of the system, and DC bus is formed by connecting the DERs and the storage through the proper DC to DC or AC to DC converters. Remember, for battery and for supercapacitor, therefore this power can flow in both the direction. We need bidirectional DC to DC converter. While as for PV panels, for fuel cell, even for wind turbine which is used as a DC output, these are unidirectional because power can flow from the source to the load or grid side, and it cannot flow otherwise. Okay, so this diagram will help you to visualize the structure of the microgrid system, and this side is a bulk power system as arrow source, and this side is a DC macro system. The power flow in presence of storage is in both the directions. The power can go into the grid, power can taken from the grid. Okay, and these are the other control issues. Maybe when we discuss more about them, then I will explore those things. Now, as you know that it is the interface of the power system, power electronics, and lot more components, and the significant role lies for the microgrid voltage source converter. Okay, so this is the grid here, these are the generation and these are the loads, this is storage, and this is the main converter, the main voltage source inverter. So as I said, this inverter has lot of importance in terms of the function of the microgrid. This inverter not only exchanges the real power from this to this side, both the sides, but it can also address the reactive power, the load balancing, the compensation of current harmonics, so and so on. Okay, so the objectives of the microgrid side voltage source converter are basically the real power sharing with utility in proportional to the available power at the DC link, and also to enhance the power quality by having features of compensation of current harmonics, load balancing, and the reactive power support. Okay, so these are the additional things. Power quality features can also be embedded into the operation of this inverter. We will talk about those things also in the coming classes. Now you may ask that what power quality issues here means. For example, the voltage rise and voltage dips could be on the grid side, can we address them, even to remain connected to the source, the load to the grid, current unbalance, excessive neutral current, harmonic and DC current injection, okay, increase in the reactive power, and then trying to use this voltage source converter to address these issues. So definitely the responsibility of this converter is much more, and its reliable operation is expected in all situations. Many times there is not only one inverter for a one microgrid system, there are many converters are used to address these issues, either in a very committed way or in a combined way. That again is decided by its operating principles or its requirement in the particular field applications. Now, as you know that this operation of the microgrid is broadly in two forms. Number one, the grid interactive mode, and second is the standalone mode. You would have heard about these two important modes. So when it is connected to the grid through voltage source inverter or converter, then obviously it is in the grid interactive mode. And if it is not connected to the grid, then it is a standalone mode. Clear? Now, standalone mode and grid interactive mode, what is the main difference? What is the difference functionality wise? Okay, the main difference is that in a grid interactive mode, the voltage source converter is always in a current control mode. In case of the standalone mode, the voltage source inverter has to act in a voltage control mode. Why it is so? Because in case of the grid connection, where the microgrid inverter is connected to the grid, the voltage is available from the grid. So voltage point is already there, and at that point we connect the inverter. So inverter injects current at that point. Therefore, the inverter is in a current control mode. So this should be always remember that any converter, microgrid converter, used in a grid interactive mode is always in a current control mode. When this microgrid is standalone mode, there is no voltage source available from outside. There is no voltage reference, there is no grid connection. So it has to generate voltage to supply the load. And therefore, the microgrid inverter will act in a voltage control mode. This is very important thing. Okay. When it will be in a grid mode, when it will be in a standalone mode, that is decided by many parameters. Mostly the voltage and the frequency. For example, in this graph, if you see the middle graph, the white portion, okay, white and this dark yellow, and this side, left side, all three regions come under grid interactive mode. This whole area. Outside this area is a standalone mode. Now what is this outside area? The outside area is the one in which the frequency and the voltage are out of the limits. For example, the voltage is less than Bg minimum or more than Bg max. The frequency is less than Bg minimum, this portion. Frequency is more than maximum value. So this region corresponds to the standalone mode, and this region corresponds to the grid interactive mode. In this region also we can classify other subcategories. For example, the grid power, excess power, or grid power, balance power, or grid deficit power. If the frequency is between the Fg min and Fg nominal minus epsilon, this is called basically deficit power because frequency is less. The frequency is more here, this is called excess power. Okay, so these things are further there to subcategorize the grid interactive mode. These things can again be further explored, but this is a general feature that I am explaining. Apart from that, if you come to the grid interactive mode, then the most important power flow modes are basically rectifier mode, inverter mode, and the zero power factor mode. So what is about these modes? It is about the power flow into the grid, power flow out of the grid, or there is no power flow but there is a reactive power support. So these 2 points are corresponding to the reactive power support. Okay, so in case of this, actually look that current flows from the grid to the inverter. Okay, and therefore the current is in a phase. The inverter acts like a load. It's like that you are giving energy back to microgrid. How this is possible? This is possible to either store the energy in the storage or to supply the local load. And in this case, the inverter acts in a rectifier mode. The second case is inverter mode, where the power flows from inverter to the PCC or to the grid. And in that case, it's inverter mode. The delta is negative here for inverter and positive for inverter here. It's a simple like B1, B2 by X into sine delta. This is the delta which is responsible for power flow. These two modes are basically 90-degree mode. So one is that current leads the voltage by 90 degree in the first case. The second case, the current lags the voltage by 90 degree. So in case of leading, it acts like a capacitor. In case of the lagging, the microgrid acts like an inductor. So these are the reactive power injection mode actually. Okay, purely reactive power injection mode. If you want to support the reactive power, then these modes are used. If you have combination of all these things, then it becomes a general operation of the microgrid voltage source converter. This is further shown here to make it more detailed operation. So we have categorized these things in a grid injection mode, the grid supporting mode, and zero grid current mode, bidirectional power flow mode. In case of grid injection, the power is injected into the grid because the generation from the renewables is much more than the local load. This is the local load here. Okay, so power from the microgrid comes here, it goes to the grid, as well as it is supplying to the load. The blue color shows that there are undesired components of the power that could be like harmonics, it could be a reactive component. This is always supplied from the inverter. In all cases, the dynamics of blue color line or injection is always same for this, for this, for this, for this. It means the reactive power components of the current, the harmonic components of the current can always be supplied from this inverter. What red color shows is the real power exchange. So in case of grid supporting, the power perhaps from the microgrid is not enough. So this power is shared between the microgrid and the grid. You can see here. Okay. And similarly for the third one, which is called zero current mode, there is no current from the grid, but still grid is there, the presence of grid is there, and the real power is supplied from the microgrid to the grid, to the load. That means there is a good enough power to supply the whole load. And the last one is bidirectional. The current is not only taken to the load, but also is given to the microgrid to charge the storage. So these are some operational modes of the microgrid. Now we will come to another important aspect, and that is about the control algorithms for converters, particularly for microgrid voltage source converter. In the grid operation in connection with the microgrid, these are important issues, that how to generate the reference quantity for the inverter or the source converter, voltage source converter. So for that, different theories are used. Okay, the most fundamental of them are synchronous reference frame theory, we call it DQ0. Then we have a stationary reference frame theory, alpha beta 0, and natural reference frame theory, ABC, which we normally use in our study and analysis, and instantaneous symmetrical component based control, 0, 1, 2, or plus minus 0. These are four important concepts which are used in power system, in electrical machines, in power quality, in microgrid operations to generate the reference currents, okay, or reference voltages. So the idea is that when you want to do something with the help of microgrid, we must know that what amount of quantity is required to be injected or to be generated, either in a current form or in a voltage form. If the microgrid is in the grid interactive mode, then we have to generate the reference quantity in current form. If the converter is the microgrid in the standalone mode, then we have to generate the reference voltage for the microgrid. So depending upon its a mode, we can decide the what reference quantity are to be realized, and these reference quantities are extracted or they are estimated using these formulations, these theories. Now apart from that, the energy management is very important. How to manage the energy flow between the load, the source, the grid, the microgrid, and the storage. At the L1 level, the level 1, we decide whether the microgrid operation should be in a grid mode or off-grid mode. That is done by checking the voltage and frequency conditions, as I have shown one graph in one of the slides. So we first decide operating mode, whether it is a grid interactive or it is a standalone. Okay. Then after that, once we decide the grid mode, if it is a standalone mode, it has to go in the voltage control mode. If it is a grid mode, then we'll go further, that whether it is excess grid mode, balanced grid mode, or deficit grid mode. This is L2 level. And then L3 is where we identify the microgrid operation mode. This is grid mode, this is microgrid mode. Okay, so remember, at level L1 we have a operating mode. Then at level L2 we have a identification of grid operating modes. At level L3 we have a identification of microgrid operating modes. And at the level 4 we generate the reference quantities to all required converters, PB, battery, supercapacitors, inverter, and for all their control. So this is a very broad hierarchy of the energy management system in the microgrid structure. If you go further, then we can think like this. We start in the big level L1, where we decide that whether it should be the grid mode or it is a off grid mode, depending upon the frequency and voltage comparing. So if the voltage and frequency is within limits, then we say, well, it is a grid mode. And if it is out of limits, then you cannot connect the microgrid to the grid, then it is called as islanded mode. Okay, as I said, at each levels we need certain controllers. Okay, and controller will take care of the action for controlling the relays, the circuit breakers, control the switching of the converters, or control the charging and discharging of the storage. So all these parameters are coordinating to each other in a certain hierarchy or in a certain communicated ways. If you look the previous discussion in terms of the controllers, then you can say the controllers are at different stages of the microgrid. For example, this is primary controller. Okay, this is the secondary controller. This is the tertiary controller. Now, what name primary, secondary, tertiary has to do? The primary controllers are the ones which are on the component side. For example, DC to DC converter, AC to DC converter, which are near the distributed energy resources here. And then at secondary level of controller, we come to the main stage of the grid between the DC, AC and DC, that is called main converter or microgrid converter, which means consists of DC to DC and DC to AC. So this is secondary level controller, because this is at the second stage of the microgrid. And at tertiary level is the one where we decide whether the microgrid should be connected or not connected, what should be the parameters of the grid, what is the frequency, what is the voltage, can we have some controller on these parameters. So this is decided by the AC side. From microgrid point of view, this is primary, this is secondary, this is tertiary. But from the grid point of view, this is primary, this is secondary, this is tertiary. But since our focus is on the grid, microgrid side, so our terminology is primary, secondary and tertiary. This is further explained here, the hierarchical structure of this microgrid controllers. So primary controller is here in the microgrid, which involves the current voltage regulation, preliminary power sharing among the units of the microgrid, system recovery under fault conditions. Secondary controllers involves about the voltage frequency restoration, power quality enhancement, energy cost, and so on. At tertiary level, we have I landing capacity. As I said, you will decide whether it will be the grid mode or off-grid mode, power management, energy management, economic dispatch, and so on. And requirement from the control point of view, the control bandwidth increases from this to this. Because as you move from the grid to the microgrid, the switching devices are being involved and the requirement for bandwidth is more. Time scale wise, it is opposite. The more the bandwidth is this, okay, the smaller is the time and more time is required for the lower bandwidth. So time scale increases on this side, but control bandwidth increases from this to this side. And this is a further description on that the secondary control, mostly secondary control is more emphasis for a power system engineer. Of course, primary is also important, but secondary we integrate both the sides, the tertiary side and primary side. So they may have different nature, maybe centralized or distributed or decentralized. Then they have another, classifications, non-cooperative, cooperative, and then there are further classifications that you can study in your either project research work or you should some other courses that is being taught at the institute. All right. So these are some references that you can go through after listening this presentation, and depending upon research interest, you can choose some of the areas in your MTech, MS, PhD, or in your BTech project work as well. So with this, I will stop the presentation part. In the next class, we will start with the PV systems and the other connected parameters.